Crystal Parameters 2. Packing Factor. In this lesson, you will learn to explain close packing in 2 and 3 dimensions, classify close packing as cubic close packing, that is CCP, and hexagonal close packing, that is HCP, determine the packing factor for SC, BCC, and FCC. We often describe very strong material as tough as steel. But why is steel so strong? Recall that in our previous session, we have seen that pure iron is not commercially useful and addition of small amount of carbon yields strong steel. Iron in its pure form is called ferrite, has a body-centered cubic structure with a poor solubility of carbon. But at higher temperatures, ferrite changes to a non-magnetic form of iron called austenite, absorbing the carbon, and forms a face-centered cubic structure. Given here is the carbon steel alloy that we have created. Carbon atoms have smaller atomic radii which fit into spaces of the iron lattice structure. Here, carbon atom, that is the solute, gets dissolved in the solvent, that is the iron lattice. So, we say that carbon plays a major role in the formation of hard steel. Varying the amount of carbon produces several carbon steels. Factors such as atomic radius and packing factor is crucial to us so that we can derive the best alloys. Let us now further explore what packing fraction is and the method of determination of packing fraction for various crystals. Have you ever been to your fruit shop to pick the fresh ones? Hope you have observed the specific arrangement that your fruit seller uses to stack his fruits. Do you find him erecting a pyramid of his fruits? But why does he prefer those arrangements? If he stacks the fruits one above the other, he will use more space. Hence, he chooses this packing so as to reduce the space occupied. This is how a metal or any molecular substance also arranges itself to take the minimum volume. Consider the atoms of a metal to be hard spheres, and on packing these spheres in one dimension, we would end up with an arrangement of atoms in a linear fashion with a coordination number which is 2. While arranging in two-dimensional packing, we can either arrange the second row of spheres one below the other, or we could also place the second row of spheres not exactly below so as to minimize the spacing. Can you see these two arrangements and the corresponding spaces created? This gap is also called a void. By nature, any metal or element tries to pack the maximum number of atoms into the minimum space. This type of packing is called the closest packing or close packing. Closest packing is further classified as cubic close packing or square packing and hexagonal close packing. Let us look at them in detail. In a close packed layer, we can arrange atoms with minimum space between them. Consider the atom A with surrounding atoms X. It has 6 as its coordination number, and a second layer of atoms can be placed in the depressions between them. Now, we see that around A, we have 6 depressions, which can be named as B and C alternatively around A. By placing atoms on depression B, do not allow atoms to be placed on depression C. Now, if we have to place the third layer, we can have two possibilities: either place the spheres above depressions of A or above C. Cubic close packing. The arrangements in which the first layer of atoms occupy A depressions, the second layer B depressions, and third layer on C depressions give a sequence of layers ABC ABC. This arrangement is known as cubic close packing, that is CCP. Hexagonal close packing. This type of arrangement, wherein atoms are alternatively placed in AB-AB depressions, is called hexagonal close packing or HCP arrangement. Apart from closed packed structures, we also have the body-centered cubic structure with a packing more open than that of closed packed structures. The packing arrangement depends mainly on two factors, such as the radii of the atoms and the type of the bond. After having understood the various packing arrangements, let us now understand the density of packing, also called the packing factor. Atomic packing factor or APF is the ratio of volume occupied by the atoms in a unit cell to the total volume of the unit cell. It is also called packing fraction or density of packing. We could also find the packing fraction by knowing the number of atoms per unit cell and find the product with the volume occupied by one atom by the total volume of the unit cell. If small v is the volume occupied by the atoms in a unit cell and capital V be the total volume of the unit cell, then packing fraction PF is equal to small v by capital V. So, this equation makes us clear that for a higher value of packing factor value, the total volume of the unit cell need to be small. A high PF value means the atoms are very closely packed in the unit cell and there is a very small unoccupied space. For a lower PF, the atoms are loosely packed and the unoccupied space is large. Given here are the three crystal systems, namely simple cubic, body-centered and face-centered cubic system. We know that a simple cubic structure is loosely packed since the atoms are placed only at the corners of the cube. Each atom has only 6 neighboring atoms, or in other words, the coordination number is 6. Here, each corner atom contributes 1/8 of itself to the unit cell, and hence the number of corner atoms per unit cell is 1/8 of 8, which is equal to 1. If r is the radius of the atom and a be edge length, then the volume of this one atom that is spherical in shape is 4/3 pi r cubed. But we also know that in a simple cubic structure, the radius of the atom is a/2. Therefore, the volume of all the atoms in the unit cell becomes 1 into 4/3 pi into a/2, the whole cubed. The volume of the unit cell is a cubed. On further simplifying equation, the packing fraction reduces to pi/6, which is equal to 0.52. This value of packing fraction for simple cubic clearly depicts that only 52% of the volume is utilized by the atoms. In a body-centered cubic structure, we have a central atom with nearest neighbors at 8 corners of the unit cell. The total number of atoms per unit cell is the total number of corner atoms plus the total number of body-centered atoms. The total number of corner atoms per unit cell is 1, since each corner atom shares 1/8 to the unit cell. The number of body-centered atoms per unit cell is 1. The total number of atoms per unit cell in BCC is 2. Thus, the volume of two atoms that are spherical becomes 2 into 4/3 pi r cubed. We have already learnt that the radius of the atom in a BCC structure R is equal to a into square root of 3/4. Further, on simplifying, we have the given equation. Now, what is the volume of the unit cell for a cubic system? Since the edge length of the cube is a, we have the volume to be a cubed and the APF becomes pi into square root of 3/8. Further, simplifying the atomic packing factor of BCC is 0.68, or in other words, 68% of volume is occupied by the unit cell and 32% remains vacant. The packing factor for a body-centered cubic is greater than a simple cubic structure. The simple cubic is not closely packed and cannot have a higher packing factor than the face-centered cubic. We have learned that a face-centered unit cell has 8 corner atoms and 6 face-centered atoms. The structure being closely packed has each atom touching 12 neighboring atoms. The number of atoms per unit cell in a FCC is 4, and hence the volume of 4 atoms is equal to 4 into 4 by 3 pi r cubed. Also, the atomic radius for a FCC is r is equal to a square root of 2 by 4. Substituting in equation 1, that is, for volume we have 16 pi by 3 into a cube into 2 square root of 2 by 4 into 4 into 4. Further simplifying, we have the equation to be pi a cube square root of 2 by 6 and the volume of the unit cell is a cube. Thus, we have atomic packing factor of FCC to be pi square root of 2 by 6, which is equal to 0.74. From this value of packing density, we understand that 74% of the volume is occupied while the remaining 26% remains empty. The packing factor for a face-centered cubic is greater than a body-centered cubic structure. Let us now work out this problem to reinforce what we have learned. An aluminium foil with FCC structure has a lattice constant of A equal to 0.405 nanometers. If the aluminium foil has a thickness of 0.004 centimeters and side of 20 centimeter, what is the number of unit cells? Here, we are given that the lattice of the aluminium has FCC structure with a lattice constant of 0.405 into 10 to the power of minus 9 meters and the thickness of the aluminium foil to be 0.004 centimeters and side 20 centimeters. Let us first convert these lattice constants to the SI units form, that is in meters. In order to find out the volume of the foil, we need to find the product of the area and the thickness, which is equal to 1.6 into 10 to the power minus 6 meter cube. We shall now proceed to find the volume of the unit cell A cube. Substituting, we have A cubed is equal to 6.6430 into 10 to the power minus 29 meter cubed. Dividing the volume of the aluminium foil by the volume of the unit cell, we have the value of the number of unit cell to be 2.408 into 10 to the power of 22. Thus, the given aluminium foil has 2.408 into 10 to the power 22 unit cells. Summary. Let us now recap what we have learned in this module. Closest packing or close packing is a type of packing wherein the metal or element tries to pack the maximum number of atoms into the minimum space. Closest packing is further classified into cubic close packing, also called CCP, and hexagonal close packing, also called HCP arrangement. Apart from closed pack structures, we also have the body-centered cubic structure with a packing more open than that of the closed pack structures. Atomic packing factor or APF is the ratio of volume occupied by the total number of atoms in a unit cell to the total volume of the unit cell. It is also called packing fraction or density of packing. In the case of a simple cubic lattice, the packing factor is equal to pi by 6. Body-centered cubic has a packing factor of pi into square root of 3 by 8. Face-centered cubic structure has a packing factor of pi into square root of 2 by 6. FCC has a highest packing efficiency of 74% and BCC also has a greater packing efficiency of 68%. But the packing efficiency of a simple cubic is very low to 52%.